Today we're going to start talking about Chapter 8, which is on vectors. So before we get started on talking too much about them, we have to know what a vector is. Now, most numbers are called scalar, and scalar numbers are those that represent one thing, such as speed. You can only go one speed. A vector is a quantity that has both magnitude, meaning an amount, and a direction. So for example, wind has a speed and a direction. That's an example of a vector. So let's look at some examples and see the difference between vectors and scalar numbers. So a boat traveling at 15 miles per hour. We just said speed is an example of a scalar number. So that's a scalar number right there, 15 miles per hour. A hiker walking at 25 paces due west. Well, I now have an amount and a direction. So this is going to be an example of a vector. Next one, a person's weight on a bathroom scale. This one might be a little bit tricky. Weight is just one number. But you have to remember that the weight is the mass of a person and the amount of gravity pushing them down, because gravity is another force on us. So weight is actually a vector. Here are a couple problems that you could try on your own. So, whole bunch of vocabulary to go over right now. So, we have an initial point is where my vector starts. Terminal point is where it ends. Okay. Initial point sometimes is called the tail, and the terminal point sometimes called the tip because it's a ray, so it's going to have a tip like an arrow. Okay. Standard position is essentially the direction at which it goes. Normally standard position is from the x-axis and goes up to my vector. The direction of a vector is the direction angle between the vector and the horizontal line. So this one right here would be 35 degrees from the horizontal line. The magnitude of this one is the length at which the vector is. That's called our magnitude. And the way we do that is we would say, okay, well, down here it says 1 centimeter is equal to 5 feet per second. So you could take a ruler and measure how long this is. According to the book, if I measured that out, that would be 2.6 centimeters. So that would be a total of 13 feet per second. Okay, so you could measure that out. Notice that magnitude is denoted as, it looks like the absolute value of A. But those two lines are magnitude of vectors. Okay? Next vocabulary word, quadrant bearing. Okay, it says the direction of a vector can also be given a bearing. A quadrant bearing, phi, looks like that. Phi is the direction measurement between 0 and 90 degrees east or west of the north-south line. So you got to think of the compass. Okay, north-south line is this one right here. Okay, and so if it said 35 degrees south, 35 degrees of east, so I'm looking at south, and I go 35 degrees towards the east. Okay. True bearing always starts from the north line and goes down towards it. So this one right here, my red, my true bearing would be 145 degrees, and it goes in a clockwise rotation. Okay, clockwise rotation. Also, it says right here, anything that measures 25 degrees clockwise from north would be written as 0, 25 degrees. Okay? So that's a lot of vocabulary to go over right away. It'll make sense as we keep going. Alright? So, use a ruler and protractor to draw an arrow diagram for each quantity described. Include a scale on each diagram. Now, I'm not going to expect you to use a protractor, but I am going to expect you to use a ruler so that you can draw your scale, because that is important for this part. Okay? So if I look at this one, it says 20 feet per second at a bearing of 30 degrees. Okay? So that's a true bearing, meaning we're starting from my north-south line right here. And I'm going to go 30 degrees this way. Okay? So I go 30 degrees. Okay? I'm going to say that that's 30 degrees. And then with my ruler, I'm going to draw just a line right there. Okay? Now, I didn't use a ruler, so mine doesn't look straight, but Essentially, that's what you're going to do right here. Okay? I'm going to label my line A because that's what they want me to. And then I could take my ruler and measure how long this is. So, I don't have a ruler that would be nice to show you on here, but essentially what I could do is I could draw a scale for mine. So let's say that I measured this on my ruler, and my ruler says that this is 4 centimeters. Well, we wanted it to be 20 feet. Okay? So if I think about it, 4 centimeters equals 20 feet. Okay? So if I wanted this down to a scale, I could divide both of them by 4, right? And so I'd get 1 centimeter is equal to 5 feet. So that's going to be my scale. So I'm going to put that over here. 1 centimeter is equal to 5. Okay? There's my scale right there. Yours is obviously going to be different because you're going to have a ruler to try yours out. Next one. Okay? V is 75 pounds of force at 140 degrees to the horizon. So that's going to be this one right here. Okay? So my horizon right here is my x-axis. I draw 140. Well, you know all the way up to the north, right here, the y-axis is going to be 90, and then another 50 after it. So here's mine right here. Okay? And that was V. Okay? I know that this amount right here is 140 degrees. Okay? And we want it to be 75 pounds. So for example, let's say that I drew my line 3 centimeters. So I'm going to say 1 centimeter is equal to 25 pounds. Because 3 centimeters then would be 75 pounds. So I'm going to write that as my scale. 1 centimeter is equal to 25 pounds. Again, yours might be different than mine, but this is what I have right here. Okay? Letter C. Letter C. Z equals 30 miles per hour at a bearing of south 60 degrees west. So I'm going to start from the south, okay, and I need it to go 60 degrees towards the west. So I draw my angle. This way is 60 degrees south of west. Okay, so that's my 60 degrees right there, and I'd label it as Z. And now they want it to be 30 miles per hour. So let's say that I found it to be 1 centimeter, and I drew mine 3 centimeters long, so that would be 1 centimeter is equal to 10 miles. Okay? Here's a couple more problems you could try on your own if you'd like. Alright? So, we got to talk about a little bit other things. Okay? Parallel vectors. Parallel vectors have the same or opposite direction, but not necessarily the same magnitude. Okay, so for example, A, B, C, E, F are all parallel. Look, they all have the same slope. Okay, all have the same slope. They might not be going the same direction. Okay, might not be the same length, but they all go the same way. Equivalent vectors have the same magnitude and direction. Okay, they have to have both the same magnitude and direction. So A and C would be same magnitude, but notice A is not the same as E because E is going the opposite way. It's not the same as B because B is longer, it's got a bigger magnitude. Okay? So those are the only ones, A and C are the only ones that are equivalent. Opposite vectors have the same magnitude but in a different direction. So for example, A and E are opposite because look, A is going this way, and B is going this way. They have the same magnitude, but just in opposite directions. So those are opposite vectors. Okay? Now, let's say we have two vectors together. For example, you're going down the river, you're paddling down the river in a kayak, you have a wind and a water direction, so that's multiple vectors pushing on you at once. Okay? There's a couple different ways that you can do it. There's the triangle method, which is my preferred way, triangle method, where you draw your one vector, add it on to the next one right at the tip, and then you end up getting some triangle, a plus b vector. Okay, that's my favorite way to do it. There is also the parallelogram method, where you would do tail to tail. So you put the two tails together, the resulting vector is going to be right in the middle of them. Okay, so that's another method of doing it. All right, so example 3. In an orienteering competition, Tia walks north 50 degrees east for 120 feet, then walks 80 feet due east. How far and at what quadrant bearing is Tia from her starting position? So I'm going to want to first have coordinate plane right there. You're probably going to want to have the same as well. Now what we can do is we can create some sort of scale factor. Now let's say that 1 centimeter is equal to 50 feet. Okay? So if Tia is going to walk 120 feet, 50 degrees northeast, okay? So 50 degrees and 120 feet, well, let's see, 120 feet divided by 50 feet, that ends up being 2.4 centimeters. So I'm going to draw my blue line, 2.4 centimeters, okay? This is 50 degrees, okay? Right? And this is 2.4 centimeters. All right? So that's Tia starting to walk right away. Next, she's going to go 80 feet due east. Okay? So again, 80 feet divided by 50 feet is going to be 1.6 centimeters. So I'm going to draw a line that's about 1.6 centimeters. And it's due east, so it's right on my east axis right there. Okay? There it is right there, and this is 1.6 centimeters. Okay? So to figure out how far she actually walks, it's not as easy as going 2.4 plus 1.6. Okay? That would equal 4. Well, that's not what ends up happening. So what we're going to do is we're going to come over here, okay? And I'm going to draw my line, okay, 2.4 centimeters at a 50-degree angle. And then I'm going to draw my 1.6 centimeters due east, so 0 degrees. And then there's going to be, what I'm going to do is I'm just going to draw a straight line from tip to tip, right about there. Okay? And then I can take my ruler and I can measure that out. Okay, so I'm going to measure that out. Well, take my ruler. You should get somewhere in the ballpark of 3.7 centimeters. Okay, so that's my value right there, 3.7 centimeters. Then what we can do is with a protractor, okay, we could measure out what this angle is right here. Well, if we measure that angle out right there, we find it to be about 66 degrees. So somewhere in the ballpark of 66 degrees. So that means how far and what quadrant bearing is Tia from her starting position? She's going to be, well, let's see, 3.7 times centimeters times 50 feet. We're going to multiply that together, and that ends up being 185 feet. And she's going 66 degrees east from north. So it'll be north, 66 degrees east. That right there is how we take care of vectors. All right, so here's another example right here. What you could do is either the triangle method, or we can try out the parallelogram method as well.